Okay, these are two equilibrium equation for the bending case. This is from vertical equilibrium when beam is subject to an external load Q. Q is a function of x, and this from a vertical equilibrium equation, and this equation is from z directional moment equilibrium equation. Those two equilibrium equation will be fundamental equations in beam theory, and for the advanced beam theory, there will be extra terms which will contribute to inertial force. Let's say this beam is vibrating, then or this beam is on elastic, supported on elastic foundation. There will be extra terms there. So anyhow, these two equations are force equilibrium, and from by observing the beam deformation, we notice that the upper skin, when subject to this directional bending moment, subject to a compressive, and the bottom surface is subject to a tension, which means that somewhere between this line there exists a neutral axis where there is no axial strain. That is called neutral axis. And by definition of x directional strain, x direction means that along these directions, x directional strain is given in terms of the curvature. Curvature is again defined as the radius of this curvature, and this position is the neutral axis, which we do not know yet, and then this any position is defined as the y. So strain at y is, by definition of this strain, defined as minus y over r, and r is the curvature, which we do not know yet, and y is the vertical axis. So epsilon x is minus y over r, and by a geometric observation, r d theta equal to dx. As you can see here, this is the r and d theta. So r times d theta will be this length. And again, this is the neutral axis, means that the neutral axis does not deform, does not contract. So these lengths should be same as dx. So from this observation, we have the r d theta equal dx. So 1 over r is defined as d theta over dx. So curvature is nothing but the rate of the angle along the x-axis. So instead of 1 over r, we use the d theta dx. So epsilon xx is defined as minus y d theta dx. Pay attention to this figure. What is d theta? D theta is this surface. Before deformation, it was a vertical, and then when it deforms, it rotates. It rotates. That's the theta. So later on, we will be able to obtain this theta as a function of the external moment and material property and cross-sectional property. So this is the all about the deformation observation and strains. What is the next step? Next step is, once we have a strain, then we need to stress. We need to use a stress. So we are simply use sigma and strain, stress and strain relations. And this relation is obtained with the assumption that sigma the other component, sigma y and sigma z, is 0. So simply one directional stress-strain relations. And then again, this strain was obtained here. And so sigma x is minus y d theta dx and times Young's modulus. That's the sigma x. Now, what is the next step? Moment, the relation between moment and stress. So next step is the moment and these stress relations. This is the bending moment relations. And so pay attention to here, there's a minus there because of the sign. This is how we define the positive moment. And so there's a minus there, then sigma xx and y dA. So sigma xx times dA is the force, and multiply by y give us the moment, and we integrate over the thickness. So sigma xx, we already have this relation and put it here. And here you need to be careful, because in integrations you have the material property and d theta dx. This material property, in this case means that the material property is always constant through the thickness, and d theta dx is not a function of cross-sectional area. So this one and this is constant, so out of the integration. But if you have different material layered through the thickness, then this E should be integrate, okay, part by part, layer by layer. So here, case is E equal constant, and we got this one, and here we have a very important cross-sectional property, y square, integration of y square. What is that? We call moment of inertia. Okay, moment of inertia. So which is called IZZ. So finally we got moment, whatever moment we apply to a beam. That beam is related to a cross-sectional property I, and Young's modulus, and d theta dx, the rate of these rotations. Okay, rate of this rotation. So d theta dx was the unknown, and now is defined by moment we apply and material property and cross-sectional properties. And I'm sure you have to remember this equation, but you also need to understand the procedure, because in exam or a quiz, you will have a beam with the different material layers. Okay, so you should be able to, what if you have the different material? Let's say the beam has the 3 different layers. Let's say A and B and A, material, different material properties. Then moment definition and exactly the same as this procedure. Only difference is that when you integrate E, Y, d theta, dx, dA, you have to be careful in integrating this term. And here, d theta dx is always constant. So dx, d theta should be constant. And E and Y is a function of simply A. A in this case, if this is the rectangular, dA is simply B times dy. What is B? B is the width of the beam. right? So when you integrate y, you should integrate by you should integrate from here separately. Okay, so you will have something like d theta dx and EA times IA plus EB times IB and something like that. Okay? Again, when you integrate this part, E times Y dA, dA is B times dy. So when you integrate this part, within this part, the material property E is a constant. So you have to integrate only this part, and then E can be constant, and integrate from here to there, and then here you integrate again, and that case E is again constant. So point here is that you have to separately integrate. Okay, separately integrate. And IA, what does I means? IA means IA is corresponding to only this area. Okay? While understanding this one is very important. So as you can see here, d theta dx is equal, given by m and I equal 1 to whatever layers. Remember, moment is defined d theta dx, and all the summation of E times y squared dA, and each material times, material property times, and II, that will be the summations, summation of these whole terms. And so d theta dx will be moment divided by summation of E material property times I. I is the moment of inertia for each layer. Okay? This is the equation. And why this is so important? Well, later on, when you calculate the stress, back to here, you have this one, right? And now you calculate this term, and let's say you have 3 layers, not 1 layer, you have 3 layers, and let's say you want to calculate the stress at a certain point. What would be your step? What is procedure? Well, from here, sigma x is simply minus y times, what was this one? This one was moment divided by whole EIII times what? See, now we want to calculate the material, the stress at this point, and you need to multiply E at that point. Let's say material property is A, B, and C, then you have to multiply A, or I'll say I, or different, I'll say J. J is the corresponding to from, well, let's say the sigma x from here to there, then material property here you should use EA, right? And from here to there, the y is certainly from here to there, and material property you have to use E, B, and so on. Why? Well, simply pay attention to here. The stress is defined as the E times strain. And these terms are all related to what? Strain. And strain was calculated from this step, right? This step. And then why we multiply E here? Well, it simply calculate the stress out of strain. So that means to calculate the stress at a certain point, you have to multiply the Young's modulus corresponding to that positions. Okay, I'm sure you have the similar homework, right? Right? And then if you plot them, stress distribution will be simple. Strain distribution will be simply like that. Right? This is a strain distribution. Strain. Strain is always linear. Okay? Regardless of different material layers. Always a strain linear. Why? Well, we from this observation, in this case, we do not make any assumption for material properties, meaning that this procedure and this observation apply to any combination of materials. So always linear. Okay, so even for this layered beam, strain is always linear. Now, to calculate the stress, what do you need to do? We need to multiply material property, and which makes this stress distribution is the something like this way and something like discontinuous, something like that. Because you multiply EA here, you multiply EB here, you multiply EC here. Okay, so stress can be discontinuous, but strain is always linear. To understand this one, as I told you, you need to be able to drive these steps: strain observation and stress strain and moment stress relation. Okay? 이거? Okay, strain, we have the beam with the three different layers, material properties A, B, and C. The strain distribution is simply, okay, I will put, oops. Strain is linear like that, right? This is the strain. This is the epsilon x, which is a function of y, linear function. Now, how about the stress? Stress, how do you calculate the stress when you have this strain? Well, simply you need to multiply a material property, right? So from here to, you have three different layers. So from here to there, which Young's modulus do you need to multiply to have stress? EA, right? So let's multiply EA. And since this is the continuous, this stress distribution will be like that, right? So this is simply E times EA. Now, from here to there, now, from here to within this layer, we have a strain, and what material property do we need to multiply? Now we need to multiply EB, which is different from EA, right? So that means E times EA, EB. So this is discontinuous like that. Okay? Can be discontinuous. Okay? So that's the point. A very important behavior. In real beam, the beam is usually made of many different layers with different material properties, and each layer, the strain is always linearly varying, but stress is stress is also linear, but it can be discontinuous like that. Okay, that was the basic theory for beam bending, and here is the summary to compare between bar, shaft, and beam, and to help you better understand each component, force and stress and cross-sectional property and so on. And the second order moment of inertia, when, as you notice, in beam theory, we have the I, ZZ, which is moment of inertia, and we need to better understand comprehensively the property of the cross-sectional property. This I, actually, moment of inertia, we have three properties, IYY, IZZ, and IYZ. And we have two different types. We need to understand two different types of moment of inertia. One is that, okay, let's say we have the moment of inertia with respect to this axis. Now, this axis has moved by ZD and YD. It's parallelly moved. And now we want to calculate the moment of inertia with respect to this axis. And how do we calculate that? Well, this is called parallel axis. This is the parallel axis theorem, and this is the final. And the moment of inertia is simply the original moment of inertia plus YD is the how much you moved and scale times A. This is the parallel axis theorem. And another important thing is that how about we have the moment of inertia with respect to the x-axis. How about the moment of inertia with respect to this axis, which was rotated from by theta from the original axis? This one, we, by definition of this coordinate system, when we rotate from one axis to the other by angle of theta, then we have a relation. And by definition of this moment of inertia, we put this in here and then go through a little bit of a equation. And finally, we got this relation. And again, this relation is exactly the same as the stress or strain transformation, and so we can use the Mohr circle to calculate IY, IZZ, and IYZ. It's like a sigma XX, sigma YY, sigma XY. So from here we can calculate, again, the principal axis is also important. What is the principal axis? Principal axis is that let's say we have a certain cross sections, and we have axis like that, and with respect to this axis, means that this axis we have a certain some moment of inertia, and also this axis we have a certain moment of inertia. And how about the product moment of inertia, which is yz, is simply y times z times dA. And if you rotate certain axis, you can always find the axis where the product of inertia disappear. So only Iyy, Izz, only those two terms are non-zero, and Iyz disappear. So that axis is called principal axis. And as you will see, principal axis is also important in derivation of the moment bending stress in a beam with arbitrary cross sections. So anyhow, next thing is that now we calculate bending stress. Bending stress means that sigma xx. How about the shear stress? Well, why do we need to consider shear stress? Well, actually in beam is subject to a two load. One is the shear load, the other one is the bending moment. And when we have a bending moment, shear force like that, and this kind of external or internal shear force, what kind of shear stress will be caused by this shear force? Those shear stress need to be calculated. So resultant is simply V, but we do not know what kind of shear stress will exist here. That's what we are trying to drive here. So to do that, first step is that pay attention to here. V means that moment is always increase. Moment always increase means that when we have a VV here, there's a moment x, there is a moment plus some moment increment on the right hand side. So this moment also, what it does cause sigma x bending stress. And as you can see here, this sigma x and this sigma x, they are different. There is some increase, right? Why? Well, there is the moment has increased by a certain amount. Why moment increased? Well, because of a V. If there's a V there, there's always a moment increase. See, everything, step is very much logically chained. So, so this unbalanced x-directional force, okay, this unbalanced x-directional force will be used to calculate the shear stress. How? Well, we simply cut from top to a certain point, a y, and consider this part, and this force and that force, x-directional force, they are not in equilibrium, right? Because simply sigma x has changed because of the moment increment, which was caused by shear force. So this one and the difference between these forces will exist at the bottom part, and this is the shear stress, and that will be in force equilibrium, and this shear stress will be simply same as this one and same as that one, and this is how we calculate the shear stress. And if we changing the y, then we calculate this shear stress distribution, and summation of all this shear stress will be what? Shear force. Okay? See, again, there are each concept are logically connected. And there is a shear stress distribution, shear force distribution, which will distribute the shear stress. Okay, what kind of shear stress distribute? Well, because of this shear force, there is a moment increment, and moment increment will cause the x-directional force, force, and that unbalanced force will be equilibrated by this shear stress, and that shear stress should be same as this one, and that again summation of all shear stresses will be a shear force. Okay? And once the understanding of this logical step is important. The final equation for that shear stress is given as simply here, like that. And VIY, okay, that's the B times tau shear stress as function of Y. And where this equation terms comes from? Well, this is simply sigma x. Sigma x is times moment divided by IY. And moment, this one was simply this moment dm, and divided by x, and which becomes the shear force V from the force equilibrium. So anyhow, this is the distribution, and this one is not easy to integrate. You have to pay attention. V and I is usually constant, so can be out of integration, but this y dA, this is not just dA, not just y squared dA, this is y dA. Okay? You have to integrate this part to calculate a certain point. For instance, when you want to calculate the shear stress at this point, what do you want to do? You need to calculate the y dA, meaning that what does this dA means? dA means here. Okay? Y times dA and integrate. That we just say Q. So Q is the function of this position, these positions. And that position is the location we define shear stress. Okay? So finally, when we calculate this Q as a function of Y, we notice that it is the parabolic distribution. So not straight and not linear, it is a parabolic. And pay attention here, where do you have the maximum shear stress? Maximum shear stress always occur at the mid-neutral axis, where stress sigma x equals 0. Okay? Shear stress is always maximum. See, again, let's say we want to calculate the shear stress at that point, at point y1, okay? Let's calculate the shear stress at this point. And that shear stress is the same as this one, and that is defined as VQ over IB. And Q is the Y dA. So what is the Y dA? Y dA is simply always from top to, at this point, integrate up to where? Up to Y1. So here, as you can see here, integration from Y1 to H over 2, top. And you can see y, there is, when you integrate, y is square. So you got this one. And as you can see that distribution is simply parabolic. Let's consider a beam with a sample, beam with clamped conditions at the left and right, subject to a P. And let's try to calculate the moment distribution, the moment and shear force. Moment is simply, and here is a 0, and here is what? P times L, right? So linear P times L minus, and here, how about the shear force? Shear force is a constant from here to there, right? And minus P. This is the moment and shear force distributions, which can be obtained from dm dx plus v equals 0 and dv dx plus q equals 0. Now, let's try to calculate the stress. This is just moment and shear force, and let's see how much stress we will get. Okay, first of all, sigma x at certain positions, and this one subject to a bending moment. How much is bending? Bending moment is this much, and sigma x is simply moment y. I'm sorry. Right? This is the moment. And so to calculate the maximum, when you apply the force like that, where will beam start to fail? Beam will fail at here, here, here. Beam will fail at this point, right? Yeah. Why? Right, moment is simply maximum. And this moment will cause a bending stress at the top and bottom. Top, in this case, is the tension, and this one is the compression, right? So let's see how much stress we get from this beam. How much stress? Well, simply, moment is P times L, right? And I is B times H cubed divided by 12. That's the I for the rectangular cross section. And y, what is the y here? Y is simply half of the thickness, right? And now, how about the shear stress? Shear stress is always distributed parabolic, at any point parabolic. And as you can see, a shear force is always constant, right? Always constant, and it is a parabolic equation. Where is the maximum? So in this neutral axis is always the maximum, and that value we already know 1.5 times v over a. See, from this one, this is the parabolic distributions. And if this is the parabolic distributions, and if y equals 0 at the neutral axis, which give us which give us what? 1 point V times BH. V times BH is 3/2 is 1.5 times. So 1.5 times instead of A, I will say B times H. Okay, let's try to compare this guy at sigma x over tau. What's the ratio? And this one, we can go further, 6 times P L B H square. Right? So sigma x is simply 6 times P L B H square. And here 1.5, and V is what? P B H. So P disappear, and B disappear, H, 1/H disappear, and which is simply what? L over H. Am I right? Huh? Yeah, I mean, this is the proportional. Well, you certainly have some constant here. So point here is that beam. So we define beam as a long compared to a thickness. So L is always much larger than H. So from this equation, sigma x is much larger than shear force, right? L over H. L is always much more than 10 times over H. So as you can see here, sigma x is much larger than shear stress. And material fail always occur when sigma x reaches the maximum. Okay, so shear stress can be always neglect. But in certain case, this shear stress can be important as well. Okay, in certain case, tau shear stress can be also important, especially for the structure with a thin wall structure. Thin wall. This is the only for the rectangular cross section. Okay. Solid cross section. But if let's say we have a hollow shaft, then this shear stress will be cannot be neglected. So anyhow, this is good to know, and this is really relate to a real beam. And as you can imagine that not just for the this kind of a cantilever beam, you can have a simple support, you can have many different boundary conditions subject to a very different load. Okay, very different load. How to calculate the stress? Well, first of all, you need to calculate moment, right? You need to calculate the moment distribution, and the maximum moment is the very important point, because always material fail at that point. Okay? So you should be able to calculate where the maximum moment occurs. Oh, so this and this, they are different. Shear stress is like that, and bending stress is like that. So I would say, okay, so location is different. Shear stress occurs at this point, and bending stress occurs at this point, the maximum stress. It's not the same position. This one and this, they are different position. So if we consider magnitude, actually I have to draw like that. Very small shear stress, but this stress is very large. Now, this step is a bending of beam with a symmetric cross-section. What is the asymmetric cross-section? Well, asymmetric cross-section is not symmetric. Well, this one, you apply the bending moment, okay, bending moment, this cross-section, and simply this one and that is the symmetric. And the bending theory we have derived is for beam with a symmetric cross-section. Now, how about the unsymmetric? Unsymmetric cross-section, or asymmetric or unsymmetric. So let's say we have a cross-section like that, and moment is applied to this way, not just symmetric axis, and this moment is applied to a certain off-axis, in off-axis directions. And now theory needs to be, the bending theory we have studied needs to be modified. And this is the little different subject. And so, for instance, we have a beam with a cross-section like that. And, well, this is the beam like that, and we apply bending moment like this. Okay, beam cross-section is, let's say, extended this much, and this is subject to a bending moment. And then what kind of a stress will be distributed here? That's the point here, okay? And simply, if this is a symmetric, only moment of inertia we need was IZZ. Now, here, we need to calculate the three of them, IYY, IZZ, and IYZ. And we need to calculate the principal axis and so on and so on. Okay, for this case, what's the step? What's the theory? How do we drive a theory? Well, this is rather complicated, okay? You have to real attention to here. Again, you have to clearly understand problem statement. Problem statement here is that beam with unsymmetric cross-section, okay? And then we apply a certain bending moment and certain direction, bending moment, and what kind of a strain we will have. That's the point here. Okay, first of all, whatever moment we apply, the beam, let's say we assume this beam will have a curvature in certain directions, okay? Certain directions, x prime and y prime. And let's assume this x-axis is the axis where we apply moment. For the symmetric cross-section, when we apply bending moment, curvature will have the same directions. Okay, bending moment we indicated by my thumb, Okay, this direction, bending moment, this is cross section, and we apply moment here. This is a symmetric, then curvature, this curved. This beam will be like that, and when you apply, this beam will be curved like that, right? Curved like that. So this curvature will be simply indicated by my thumb directions. Same way as we define beam bending moment. But if this cross section is not symmetric, means that this way or triangular and so on, when we apply bending moment, this guy cross section is bending this way, not this way. Do you understand? So with the beam with arbitrary cross section, when subject to a bending moment this way, then even though we apply moment here, the curvature can be generated this way. I wish I have some. Do you follow me? Okay? Understanding of this behavior is again observation of beam bending, deformation. So the theory will start from this bending theory, the deformation. So we are back to deformations. So pay attention to my arm, okay? This is a symmetric, when we apply bending moment, this will just rotate like that, okay? Beam just rotate like that. But let's say this guy is unsymmetric, is some unsymmetric. I would say this way, okay? Unsymmetric. When I apply the same moment, but this guy it deforms like that. Not this way. Even though I apply moment this way, this behavior, these things will deform like that. Okay? Deform like that. Do you follow me? Yeah. It's different from this way. Do you remember that d theta dx this way? D theta dx and come here. Okay, hold my hand. So this way, when we apply bending moment here, this one we make one plane, and there was the center of rotation, curvature, right? So that way we define the bending moment, curvature. So bending moment and curvature is the same plane. Now this one has the unsymmetric. When we still apply same moment, but this one is a totally different curvature. So this plane has been rotate. So that kind of behavior was denoted by these two angles, two arrows. This is the way we apply, but this cross section is deformed like that. Okay, deformed like that. So Y is the denoting center of the curvature. When this was symmetric, this blue and this red was the same axis. We apply this one, and this one this way was the center of rotation. Okay, this observation, this understanding is the critical. The rest of them is just mathematics. So anyhow, curvature is defined 1 over rho. Actually 1 over rho is the r. You remember r? And d phi dx, instead of x, now we use the s. So anyhow, is again, we have a little different axis. We apply the moment, and the curvature has these two different axes. And these two different axes, we simply have a coordinate transformation m and n and y and z. This one, m and n. Okay, forget about this one. This one and this is a two different coordinate system. I don't want to confuse you. Forget about this one. This is the cross section. We have the y and z, and we have m and n. So we apply the moment in arbitrary directions, and this m and n is for the curvature direction. So let's say this is a theta directions, and this between y and m or z and n, we have a certain this relation, right? And this is the point. Epsilon x, okay, epsilon x is always relate to m. And d phi dx. Remember d phi dx? Same as here, m. What is m here? Because of strain is always defined by, when we rotate this way, this vertical axis is the m. Previously, vertical axis was the y, right? But now deformation is like that, and so this cross section is rotate this way, so always proportional to m axis. Okay, m is the vertical axis with respect to this curvature axis, and denoting the curvature axis. So simply like that, and sigma x is times E, and this one, and this is the equation for neutral axis. Here, we do not know yet what is the theta here. We have the y and z axis, but we don't know yet. We don't know what is the m and n. We just assume there is the m and n axis, and where we define curvature and where we define x directional strain, because x directional strain is nothing but geometric definition. Okay, so what would be the next step? Next step is simply my. We have two equations, my and mz. What is my and mz? Well, we have a resultant moment like that, and we decompose this one as this way and that way. We can have two component moment which are known moment. So moment z and moment y, which we decompose in m and z direction and y direction. So moment y and moment z, and sigma x was defined in terms of a strain, right? Strain is in terms of a coordinate m, okay? But what we know is for the x and y direction. So this is the relation. And what we know here is that sigma x was coordinate m, right? Because of a strain. So m and z and m and y. And then m and z, we have the relation for the coordinate relation. This one, coordinate transformation. So instead of m, instead of n, we substitute this yz relation to here. So y and z. So zz give us yy, and yz give us iyz. And you see this cosine theta and sine theta, they came from this one. Okay? And now moment z, same procedure, but here the moment z is defined sigma x times y. Okay, I better have this one. This is the moment y, and this is the moment z. Actually, this moment y and moment z is a decomposition of this one. So you may forget about this mb. Okay, we have the, let's assume we have a moment y and moment z, and this one is, this distance is a simply z. This is a simply distance y, and moment y is the what? Moment y is simply z times sigma x. Z times, what is z? Z times this distance times this sigma x. Okay? And moment z, you multiply sigma, y times sigma x. Okay, so you have these relations, moment y and moment z. And now here, what are the known value here? Knowns are this moment y and moment z. These are known, right? So here, what are the unknowns? Unknown is this rho. Actually, I should have wrote down r. Remember that radius curvature r? And theta. R and theta, they are unknown. So we just inverse this matrix, and then theta, cosine theta, r rho, cosine theta rho, and sine theta rho can be obtained from these two equations in terms of these two moments. Okay? So, and once we know these equations and put it into here, remember this is m is here. So that's why we have this one. So rho cosine theta and rho sine theta, and we put it here and put it here. Then sigma x is simply given in terms of moment y and moment z, and all the moment of inertia. And how to calculate this neutral axis? Neutral axis here, this is simply defined as the sigma x equals 0. So sigma x equals 0 give us these equations. And as you can see here, this is yn and x linear equations. A little complicated, huh? So now here, if I, y, z equals 0, let's assume I, y is equals 0. Then this term will disappear, this term, and this term, and so on. So final equation will be like that. Don't get disappointed, okay? And I know it is a little complicated, but as you can see here, this is the moment you apply, moment z. So which one was the moment y? Moment y you apply, moment z apply. And you remember that moment y. Remember that when we apply moment z, sigma x was simply minus I zz moment z y. You remember this one, right? You certainly remember this one. And again, when we apply moment Z here, the stress at a certain point here, it will be simply Y times and IZZ and this one, right? Okay, now forget about this procedure, okay? I will give you a big hint how to calculate the stress. You don't have to go through all these complicated procedure. This is the point I want to emphasize. Now, here we apply moment Z. How do you calculate the stress at this point? Well, stress is simply moment Z divided by IZZ and vertical distance. Am I right? Okay. Now, how about when we apply moment in Y direction? This way. Then simply moment Y divided by IYY instead of IZZ, and instead of Y there will be a distance Z. Right? Distance Z. And here you have the plus sign, you have a minus sign here. Why? Because when we apply moment to this one, the upper region will be compressed. That's why we have a minus there. But here, when we apply moment here, this positive part will subject to tension, right? That's why we have a tension here. So this is the equation you need to remember. Well, again, this one is you already has the derivation here, so not much different from basic beam theory with the symmetric cross section. Okay, point here is that how do we get IYZ equals 0? Principal moment of principal axis. How YZ equals 0? Do you remember that how you get the principal axis for the cross section? So point here is that you have the axis, you have this moment. All you need to do is calculate, let's say y prime x prime. This is the principal axis, and decompose this moment into a principal axis. Okay, principal axis. Decompose the moment into principal axis and use this equation. Because in principal axis, all these terms, I, YZ, just disappear, and divide by, and so on, and simply you get this equation. So rather than using these complicated equations, you need to find the principal axis where the product of moment inertia disappear, and what you need to do is that you calculate the moment component in principal directions, and this term and that term, which is called moment Y and moment Z, right? And then use this relation. Okay? So, but I want you to go through this procedure at least once, and you need to fully understand this procedure. Even though you don't have to use this complicated equation in calculation of stress, but again, you need to understand this procedure. Okay, so that is about the bending stress for unsymmetric cross section.